Hello and welcome to Lecture 1 of Changing Magnetic Fields in Phys 1204. In this video lecture, we're going to see that something somewhat unexpected happens when conductors move through magnetic fields. We're going to start with an observation. Here I have a wire hooked up to a voltmeter, and notice that it is just a wire. There's no power source at all. It's just a wire going to the two terminals of this voltmeter. And now I'm going to move the wire back and forth between the poles of this large magnet. And notice that there is a potential difference detected by the voltmeter when I do this. In particular, notice that when I move the wire one way, this way, the measured potential difference comes out negative. But when I move it the other way, the measured potential difference comes out positive. And the final thing to notice is that if I hold the wire steady in between the poles of the magnet, then there is no potential difference detected. Clearly something is going on with magnetic forces. So let's think of a simple situation of a conductor. Let's say it's a rod for simplicity, and it's moving through a region with a constant magnetic field. So as in the picture, I'm thinking of a B field into the page and the velocity vector to the right. Note that the electrons, which are moving to the right, will feel a magnetic force down. You can use the right-hand rule for forces on charges and verify that. However, for simplicity and so that the signs are easy, I'm going to, as usual, pretend that what's moving around inside the metal is positive charges. It's going to make no difference. So the magnetic forces on those positive charges are up. And that's going to lead to charge separation, because positive charges move up to the top of the rod and it becomes positively charged, and the bottom of the rod is left negatively charged. These charges moving around in the rod and establishing a charge separation are going to quickly come to equilibrium, because as they move and the charge separation occurs, there is now an electric field inside the rod because of that separation of charge. And note, we've already established the magnetic force on these charges is up. The electric force on these charges will be in the direction of the E field, down. And so, rather quickly, equilibrium is reestablished when the net force on the charges is 0. As usual, wherever there's a separation of charge, there's a potential difference. And so if we were to attach a voltmeter to this rod, attached to the top and bottom, we would find that the top is at a higher potential than the bottom of the rod is. Let's use what we've just seen to explain the signs of the potential differences read by the voltmeter when I move the wire between the poles of this magnet. So first, when I move the wire down between the poles, and note that this is the north pole. So the B field is this way, and the velocity is this way. And so if you do the magnetic force in the direction of V cross B, you will confirm that positive charge is coming out, because that is the way that the magnetic force is on positive charges in the wire. That means the positive charges are coming this way. And so we have a separation of charge with positive charge here and negative charge here. And so this is the low potential side of the wire, and this is the high potential side. And notice that this low potential side is the one that's connected to the positive terminal on the voltmeter. And so that's why the reading is coming up negative. On the other hand, when I bring the wire up, now the magnetic force on positive charges is in, which is putting positive charges on this end of the wire, so this is the high potential side, and so the voltmeter is reading a positive potential difference. Well, let's check that you're understanding this so far. So now suppose we have a magnetic field to the right, and we have a metal rod that is moving to the right through this magnetic field. Which end or which side of the rod is going to end up positively charged as a result of this?